Hello everybody. So today we will discuss about hybrid renewable energy standalone systems. Okay. So as you can see the outline of the presentation, first we will be discussing introduction, global warming situation in North Canada and Quebec, optimizing the use of diesel generators. So this thing is very important because there are so many communities in the north of Canada, north of Quebec, they are not connected to the main grid. And those communities are 100% dependent on diesel generators for many decades. For many decades they are using diesel engines. So why? Because during the winter time in the north of Canada, temperature may go to -40, -50 degrees centigrade. So if you use 100% renewable energy and during the night time there is no sun and if there is no wind, so it will be very difficult for the people to survive. So they are using diesel generator for many generations. Now the efforts are being made to optimize the use of diesel generators because it is polluting a lot, it costs a lot of diesel consumption. So efforts are being made to reduce the dependence on diesel and to reduce the cost by integrating the renewable energy sources with the diesel. So those are standalone systems, right? So we will see wind and solar radiation profiles in Canada and Quebec, problems related to renewable energy sources, wind energy conversion exploitation technologies, microgrid in hybrid standalone systems, and then we will discuss different configurations of hybrid energy based standalone systems. So many researchers, engineers, companies are working on hybrid standalone systems around the world. And few years back we were doing a survey and we found that 60 different types of configurations are already being used by the engineers around the world. So it is very interesting thing to see. So coming to the global warming, as you know, year 2024 was the year of record heat. 2025 was not that hot as year 2024. And then we are talking about the pre-industrial temperature, 1880, when we started keeping the meteorological data, temperature data, weather data, all those things in 1880. So efforts are there that we have to keep less than 1.5 degree. It should not, temperature rise should not go above 1.5 degrees centigrade above the pre-industrial temperature. And if we don't do that, then it may be very catastrophic for the whole world. And why it will be catastrophic? Because many island nations may be finished. Okay, so decade 2010 and 2019 was the hottest decade ever recorded. And now 2020 to 2029 may break that record. So that's why around 10 years ago, December 2015, a conference was organized. This conference is going on for many decades, and that was 2015 was the COP21. COP21 conference organized by United Nations in Paris. An agreement was signed. 196 countries signed that agreement, and that is called Paris Agreement. And in that Paris Agreement, what was decided that we have to keeping the rise in temperature below 2 degrees centigrade above pre-industrial levels, 2 degrees centigrade. So at that time, 10 years ago, they said, okay, 2 degrees, because people were not agreeing to 1.5 degrees centigrade. So that's why, because everybody had to sign, so it was agreed 2 degrees centigrade. So that was the thing, that we have to keep the rise in temperature below 2 degrees centigrade. This was decided. Otherwise, if we don't do anything, as I thought, there will be drought situation at many places, sea level will rise, many island countries may be finished, they will be underwater if sea level will rise. Many coastal cities will be underwater. You know what happened in Louisiana and New York also, sea level will rise, so many communities will be finished. So that is the main problem. So what was there in that agreement? That $100 billion every year has to be raised for different projects fighting against the climate change, to reduce the production of greenhouse gases. $100 billion every year has to be raised, and every country has to keep the record what they are doing, how much they are investing. So at that time, China was the biggest polluter 10 years ago, and now also I think China is, because I was traveling in China, different cities, Beijing, places, other Shandong, and there was pollution as bad as in Delhi. Okay, so China is polluting, 20% pollution of the whole world comes from China. And then United States around more than 17%, and Russia 7.5%, European Union 9%, India 4.1%, Canada 1.95%. So at that time, while signing the Paris Agreement, they made a list and they mentioned this thing, which country is polluting how much. Then in 2021, COP26 was organized in Glasgow, and there they agreed that instead of 2 degrees centigrade, we should keep the limit at 1.5 degrees centigrade. And it was considered very serious matter at that time, that 2 degrees centigrade is not enough, we should go for 1.5 degrees centigrade. In Glasgow agreement they signed, and by mid-century we should have the net zero, global net zero. So global net zero means total emissions are equal to or less than emissions removed from the environment. That is global. So by 2050, mid-century means around 2050, that was agreed. So 200 countries signed the Glasgow Agreement. So there were other things in Glasgow Agreement, I will not go, you can just see. And $100 billion was still there, $100 billion every year has to be raised. Then last year in November 2024, in Azerbaijan there was COP29 took place. And again in COP29 they emphasized that we have to keep 1.5 degrees centigrade. And another interesting thing was that every year $300 billion has to be raised starting 2035, $300 billion. And that money should come from developed countries to provide money to poor countries so they can fight the climate change. But I don't know what, recently this COP30 took place in Brazil, so I am not aware what is happening there, but this is what happened last year in Azerbaijan. Now, if you see the situation in Canada, if you go in the north of Canada, so much ice and snow, people can make igloo and live inside it to protect themselves from the wind. So, and then in Montreal, many times, it has not happened after this COVID, but before COVID, every year there was a ice village used to be formed in Montreal. There's an island. Montreal is an island, and there are very small island there. Montreal is surrounded by the St. Lawrence River. St. Lawrence River is a very big river, and there is a small island. There, big national park is there, and there they organize ice village. Every 2 years they organize ice village. So what is there in the ice village? You will have big size, full size hotel made of solid ice. And there are rooms. You can go, you can rent a room there in that hotel, $200, $300 a night. And that room is made of total solid ice. Your bed will be made of solid ice. Table and chairs made of solid ice. Even the wall hangings, beautiful, colorful painting made of solid ice. And then you go to bar area and you can have a beer in a solid ice mug. You can have beer in that. And then there is a church, total functioning church made of solid ice. Table and chairs made of solid ice. So it is so interesting. Then you will say, what is this global warming? In Canada, if we have, instead of 2 degrees centigrade, we have +4, +5 degrees, it is good for Canada. Because temperature is already so low there. But I tell you, see, these are the photos of the hotels made of solid ice. Big. But I tell you, that is not good for even Canada also, this rise in temperature. Canada has 20% of total fresh water resources of the whole world. So much fresh water resources are there in Canada. And there are so many glaciers. There is one Athabasca Glacier near Calgary. I was doing PhD in Calgary 40 years ago. And we went there to see the Athabasca Glacier. What was that glacier? It was 1,000 feet of solid ice. For hundreds of kilometers, solid ice glacier. So there used to be a big truck with big wheel and those things. They take you to the top of the glacier and you can go and stand on the 1,000 feet of solid ice, and if you go in summer, sometime it melts and you can see the water is going somewhere, and then suddenly it disappears in some hole or something. So that was the time 40 years ago. And then they had the marking, okay, until 1945 the glacier was up to this point, 1955 glacier was up to this point. Then I went there in 1985, so then 1985. So it was more than 1 kilometer, 2 kilometer, 1 or 2 kilometer. At that time, 1985, 1,000 feet of solid ice of hundreds of kilometers was already melted at that time. So you see, the glacier was receding, melting. And then I went to 2007, and then in 2024, last year, again we went. Okay? What happened? Okay. So then we went, me and my wife, we went to Calgary, and we drove to Athabasca, that is Athabasca Glacier. So there we saw another miles and miles of glacier is melted. And the guide told us, now it is not 1,000 feet of solid ice, now it is only 600 feet of solid ice. See, glacier is melting. And all the fresh water comes from those types of glaciers. From Athabasca Glacier, there are 3 rivers. One is the Athabasca River, another is Saskatchewan River, and another is Columbia River. 3 river systems comes out from this glacier. So if this trend continues, maybe in few decades that glacier will be finished. All the glacier will be melted. So from where the fresh water will come? So this is not a good situation even for Canada. If you see this greenhouse gas emissions in Canada, so these are from various sectors, oil and gas, transportation, building, from where this greenhouse emission is taking place. But if you see for electricity generation, greenhouse gas emission taking place for generation of electricity is decreasing. So here you can see this is decreasing in Canada. It means less and less oil and gas and those things we are using, fossil fuel we are using. And if you see the situation in North Canada and Quebec, there are so many remote villages, and in winter time they are buried in snow and ice. They are not connected to the grid. So they are totally dependent on the diesel generators. There are many water pumping stations, they are dependent on diesel generators. There are many mines in the north, they are totally dependent on diesel generators. And then there are communication stations, okay, telecommunication, then petroleum station, there are many islands. So there are so many communities, those are dependent on diesel generators in Canada. So you cannot avoid you see so many communities in the north, they are not connected to the main grid is basically here, okay, at the border of United States, so most of the big cities are there. So that is not a problem, but in the north, they are not connected to the grid. So they are totally dependent on diesel generators, northern communities. And diesel generator, as you know, it is very inefficient. It generates a lot of greenhouse gases, and the fuel prices are very high. For example, I tell you, I live in Montreal and I am paying 7 cents or 8 cents per kilowatt hour for the electricity. But the price of electricity for these northern communities, in some broke this. Oh, seat is broken. Okay. So, in the north of Quebec, yeah, everything is fine. So, in the north of Quebec, it costs 43 cents per kilowatt hour, while I am paying 7 cents, 8 cents per kilowatt hour. And in some communities further in the north of Canada, they pay 90 cents, 92 cents per kilowatt hour for the electricity. So in the Quebec and northern Quebec communities, the cost of electricity is 43 cents per kilowatt hour. But those are the poor communities, poor people. How can they pay that much money? So Hydro-Quebec has the obligation to provide electricity to all citizens at the same price. So they cannot ask 42, 43 cents from those poor people while I am paying 7 cents or 8 cents. So Hydro-Quebec subsidize. So in that process, every year Hydro-Quebec loses around $150 million to subsidize electricity for those people. Now you will say, why it is not connected to the grid? So according to Hydro-Quebec, few years back they were saying it costs around $1 million per kilometer to put a transmission line. So if there is a community of 200 people around 400, 500 kilometers away, it means for 200 people you will be putting 500 kilometer line which will cost you $500 million. just for 200 people, which is not economical. So that's why they are keeping using the diesel engines. But now what is happening is that there are projects, we are trying to integrate the renewable energy with diesel generators. So that's why the system we are talking about, hybrid standalone renewable energy system. So diesel engine, first thing is to increase the efficiency of diesel engines. So as you can see, there are two types of diesel engines: fixed speed diesel engines and variable speed diesel engines. So fixed speed diesel engines, this technology is there for many decades. Okay, it's or simple technology, but there are some drawbacks that most of the time it runs at a light load. So if it is running at light load, efficiency is very poor, fuel consumption is lot, and it makes lot of noise, and it generates greenhouse gases. So there are some problems with fixed speed diesel generators. So a lot of work is going on variable speed diesel generators. So what are the advantages of variable speed diesel generator? Reduce fuel consumption, increase conversion efficiency. Those are the advantages of variable speed diesel generators. So as you can see in this diagram, this is the percent of load, and here the fuel consumption, percent of fuel consumption. Suppose the diesel generator is loaded at 100% capacity, then efficiency is very good. But if you reduce the load, suppose you have 30% load, you have 30% load, still you have 50% of fuel consumption with fixed speed operation. So red line is fixed speed operation, blue line is variable speed operation of diesel engine. So if you have a variable speed operation, if you have 30% fuel consumption, so there is a big advantage, there are a lot of savings if you are using variable speed diesel generators. So this is what it is being done nowadays. For last 10-15 years, the Canadian government, we are trying to integrate the renewable energy kilowatt hour per kilowatt of solar potential, yearly solar potential. If you see the installed capacity, so wind power capacity in Canada is around 15,000 megawatt total wind, and total solar capacity around 6,500 megawatt capacity. And if you see the province of Quebec, this is the Quebec. In Quebec, wind energy is around 4,000 megawatt. So as I told you earlier, in Quebec, we have 40,000 megawatt of hydropower and 4,000 megawatt of wind power. So 100% we have renewable energy in the province of Quebec. And then you will see how much is the solar? 15 megawatt. So I told you the reason yesterday what is happening. But in other provinces, we have around 2,800 megawatt of solar. See, it is not that bad in other provinces. In Ontario, this is Ontario, we have 5,500 megawatt of wind energy. So as I was telling you, we will say, okay, in India, we will see the data. Okay, we will see the data later on. If you see the wind, total world wind energy installed, it is more than 1 terawatt of wind energy installed in the whole world. Okay. And if you see in China, this is 2023 data. In China, you have 442 22,000 megawatt of wind energy. But here in this slide it is in India 44,736 megawatt. But I was checking yesterday on internet that in October in India, installed wind energy capacity in October 2025, it has reached more than 53 gigawatt, 53,000 megawatt in India. Wind energy, wind turbines are installed. And in China, wind energy capacity 520 gigawatt of wind. So it is much more than this. If you see the solar power installed in the whole world, 1.4 terawatts in 2023. And if you see here, China has around 610,000 megawatt of solar installation. So yesterday I was checking, because this is 2023 data, but I was checking on internet yesterday. In October 2025, India's installed solar power capacity was 129,000 megawatt. So much more than whatever is given in this curve, because for the last 2 years, lot of development in India and in China, 1.1 terawatt. So this is what happened. I was showing this slide in China to some engineers in a company and in some universities. So they were objecting, no, this is not right. We have already caused 1 terawatt of solar installation, and they were perhaps right. So this is what the information I got. So a lot of work is going on in India and China. Now, what are the problems related to the intermittence of the renewable energy sources? Because with the temperature, humidity, altitude, topography, atmospheric pressure, all these they impact on wind speed. Thus, the quality of prediction of the power produced by wind turbine is highly dependent on prediction of wind speed. So that's the problem. Wind speed is fluctuating and unpredictable, and at the same time load is also changing. So you see, wind speed is changing, load is changing. So basically they are not compatible. You cannot connect directly the wind energy to the grid. Same thing is the photovoltaic output. Sometime sun is there, sometime cloud is there, sometime pollution there, so less energy reaching to the solar pollution. So, and in the night time there is no sun also. So that's the problem. So that's why renewable power need processing using power electronic converters before being fed to the consumers. So energy supplied by renewable energy, so it needs a DC or AC conversion before being injected to the microgrid, because consumer needs regulated voltage and frequency. So you need power converters. We have seen yesterday so many power converters you use to integrate wind energy and solar energy to the grid. Although there are some losses in power converters, but after all this is a free energy, so it is not a big thing. And on top of that, you have multifunctional capabilities of power converter. So as I was telling yesterday, that it is not just power converter transferring the wind energy or solar energy to the grid, interfacing it, but at the same time your interfacing inverter converter taking care of the power quality on the grid. They can have, you can have harmonic compensation, right? You can have voltage regulation, reactive power compensation, load balancing, so many things you can do with a single inverter. So this is what I always tell my students doing research in this area, that you just don't have to see how much power is transferred, but it has to take care of multi capabilities. It has to take care of many problems, to solve many problems on the grid. because most of the time your converter inverter is not loaded to the full capacity. So most of the time it is 50, 60, maximum 60% capacity. So rest of the capacity you can use to improve the power quality problems on the grid. Then if you see the desirable characteristic of electrical machines for renewable energy, it should have a high efficiency over wide torque and speed ranges, high power density, wide speed range, high reliability, maintenance free. So these are the quality you look for the machines which you are using for generation in wind. High robustness, good voltage regulation, high power factor, low cost. So all these are the desirable characteristics of the electrical machine used for the renewable energy. You already know so many different types of generators are available, which are already being used by different wind farms around the world. You know, squirrel cage induction generator, it is very robust, right? So, and cheap. So it is being used a lot. But however, you know, there is a problem that you cannot have the speed control there through the rotor. So basically it is difficult to have MPPT, maximum power point tracking, with those unless you use a full size back-to-back converter on the stator. Then it will increase the cost of the system, right? And then if you have a wound rotor synchronous generator, this is the classic machine. So on the rotor side, you have 2 slip rings and 2 bushes, and you can control the active and reactive power here at the terminals. But then here again, you have to connect, because if it is connected with the wind turbine like this, the speed will be variable. Then the voltage and frequency here will be variable, right? So you need full size back-to-back converters to connect it to the grid. Now doubly fed induction generator, yesterday we saw it in detail, that on the rotor side you have 3 slip rings and 3 brushes, and here you have 2 back-to-back converters, and then it is directly connected to the grid. This is what we discussed yesterday, right? This is a grid here. But the advantage here is that these back-to-back converter are around 1/3 capacity of the machine. So like Hydro-Quebec started with 1.5 megawatt size doubly fed induction, because in Quebec, the Hydro-Quebec is using doubly fed induction generator for all the wind farm to generate 4,000 megawatt of wind energy. Initially they started in 2007 with 1.5 megawatt machines with 500 kilowatt, 2 back-to-back converters. But then with the development of technology, the FIG machine, they started using 2.6 megawatt, and now they are using 3.6 megawatt of doubly fed induction generator in the system. And then PMSG, like yesterday we discussed, you have permanent magnets here, and then because with the variable wind, the frequency will change here, so you need 2 full size back-to-back converter. So if this machine is of 5 megawatt capacity, you need 5 megawatt capacity this converter and 5 megawatt this converter, so it will increase the cost. And on top of that, you have permanent magnet, which may increase the cost of the machine. So overall cost of the machine is increased. So this is what actually, it depends how much money you have, how many machines you have bought, how you can negotiate with the company which is providing PMSGs and those things. So this all depends on that. And then another type of machine, synchronous reluctance machine, which is becoming very popular, and it's available in this capacity, 0.75 kilowatt to 450 kilowatt, made by ABB. I think now ABB, at some places they have changed the name Hitachi Energy, but perhaps this motor. So this has lot of advantages. Stator is same as that of 3-phase induction machine or synchronous machine. Rotor is salient pole construction, Saliency is created by the flux barrier of high reluctance path. So you see, these are flux barriers here, so which creates the saliency here. Okay, robust construction, less losses than induction generator as rotor rotates at synchronous speed. Okay, thus rotor currents are negligible. Rotor is completely magnet free, so this is a big advantage. So this is cheaper than PMSGs. Procedure of voltage buildup is same as self-excited induction generator. External capacitor is required. And then I was visiting in China, and there is a work going on to improve the performance of synchronous reluctance machine. And although I also have one PhD student, girl PhD student, she is also trying to improve the performance of a synchronous reluctance machine as a generator or a motor by putting a little bit permanent magnet here, a small amount of permanent magnet here. So this is what is called permanent magnet assisted synchronous reluctance machine. Many researchers are working in this direction because this machine is cheaper, and if you put little bit permanent magnet on those things, so it gives very good performance. So my student is also working in this area, and she just started 1 year ago and she is doing good. And then I was visiting China also. China, they are working also on the same type, like to improve the performance of synchronous reluctance machine. So if you see the wind energy exploitation technologies, type A, type B, I think yesterday also we were discussing about the type C and type D. Type A, you see this is squirrel cage induction generator, right? And you have this wind turbine gearbox you need, and you can connect it directly to the grid. But to start, to have a soft start, because you already know that induction generator or motor, when you start, it takes 5 to 6 times of rated stator current. So it draws a lot of current, reactive current from the network. It may generate voltage sag condition, as we discussed the first day, this thing. So to have a soft start, you can have this, and once it starts, then you can bypass this converter. Okay, so this is type A. Type B, so again the same problem that it is difficult to have MPPT with this type of machine because you cannot vary the speed. Now type B, this is wound rotor induction generator. So the same thing, the only thing is that you have 3-phase variable resistance in the rotor circuit, right? We were discussing yesterday, so it will change the characteristic in first quadrant and second quadrant. First quadrant is working as a motor, second quadrant working as a generator. So we were seeing that characteristic like this. This is first quadrant, this is second quadrant, third quadrant and fourth quadrant. This is motor, generator, something like this, as you have studied in your undergraduation. And with the resistance in the rotor circuit, it will change the characteristic like this. So you see what basically you are doing. This is the, you are using this machine as a generator. So for MPPT, you are exchanging the range, you are having the range of speed where you can do MPPT by putting extra resistance in the rotor circuit. So this is type B. Then type C we have already discussed yesterday, doubly fed induction generator with gearbox, and then back-to-back converter of 1/3 capacity on the rotor side, right? This we have discussed. And then type D is the permanent magnet PMSG machines, and you don't have to use gearbox as we were discussing, but you have to have full-size converter, back-to-back full-size converter connected on the stator of the machine, and it gives very good performance, this type D, but it is costly. But you can have full fault right-through capability, low voltage, high voltage right-through capabilities, because it is totally decoupled because of the back-to-back full-size converters here. So we already know the cost, performance, what you need in your wind farm, but as far as Quebec is concerned, my home province in Canada, they are using this type C type, using doubly fed induction generator. But as we discussed yesterday, the technology for off-grid system, no, not off-grid, C, what you call it, offshore wind turbines for large generators, 10 megawatt, 13 megawatt, 14, 15, even they are trying to develop 20 megawatt PMSG machines. Okay, so those are PMSG machines for offshore applications. Okay, now coming to our point, hybrid standalone power electronic systems. Okay, this is the example of AC standalone microgrid. So you have AC microgrid here. Okay, so here you have diesel generator, fixed speed diesel generator you have. Okay, so voltage and frequency remains constant here on the AC bus. Then you have wind turbine, squirrel cage induction generator, for example, if you have, but if you, with this machine, if you want to have MPPT, you have to have full size back-to-back converters and inverters. Okay, so this now you can use hydro turbine with squirrel cage induction generator, right? This is PV photovoltaic DC to DC converter to have MPPT on PV, and then you need DC to AC inverter to connect it to the AC bus with having constant voltage and frequency. You can have battery bank DC to DC converter for charging, discharging battery bank, and then you have inverter here. So if DC loads are there, you can connect it here. If you have AC loads, you can connect it to the AC bus. Okay. So this is just an example of AC standalone. Similarly, you can see the DC standalone microgrid. So this is DC standalone microgrid. Standalone means it is not connected to the grid, right? Standalone means it is not connected to the grid. So our topic is hybrid standalone system. So that is why I am emphasizing on off-grid system which is not connected to the grid. So here this is DC bus. So you can have PV here and DC to DC converter. See, you don't have to have an inverter here. So you can save money, right? If you have this squirrel cage induction generator, you can have AC to DC converter to connect it to the DC bus. Then you have AC load and everything, battery bank, you see DC to DC converter. So this is an example of DC standalone microgrid. Then there are lot of hybrid AC DC standalone microgrids. So you have AC bus as well as you have DC bus. The generators and load which are DC in nature, they will be connected to the DC bus, and the generator and load which are AC in nature, they will be connected to the AC bus. And it means between AC and DC bus you have a bi-directional converter. So power flow can take in any direction, either in this direction or in this direction depending on the situation. So that's how you can save a lot of money. So if you see the comparison between AC and DC microgrid, advantage of AC standalone microgrid, utilizing existing AC grid technology and off-the-shelf product, and well-established protection and standard, because AC grid is there for last more than 100 years, right? Disadvantage of AC standalone microgrid, every time you have to do synchronization, stability problem, need for reactive power, power quality problem, those things are there. So these are the disadvantages of AC standalone microgrid. If you see the advantage of DC standalone microgrid, all disadvantages of AC standalone microgrids are not present, like synchronization. You don't have to do synchronization with DC grid, right? You are not worried about the reactive power compensation and those things. most environmental friendly uh, distributed generation such as photovoltaic, fuel cells, variable speed wind power system generate DC power, and most digital loads require DC power. Okay, it can eliminate AC, DC, DC, AC conversions. And in terms of, it has the advantages over in terms of efficiency because less conversion, because of, and then cost and size. And there are disadvantages of DC standalone microgrid that you have to see the protection circuit and other things for DC voltage. Same way, there are so many advantages of hybrid. So that's why a lot of work is going on, hybrid AC-DC standalone microgrid, because if you have AC load or AC generator, you connect to the AC grid. If you have DC load or DC generator or batteries and those things or PV, you connect to the DC bus, and in between the two you have bidirectional converter. So you can save lot of money by saving lot of power conversion. So it is more efficient. But however, there are disadvantages of hybrid AC because energy management, control, operation are more complicated in the hybrid system. There are so many topologies. Okay, few years back we were doing the survey of those. So as I told you, we found more than 60 topologies which are already being used by different engineers around the world. So these are the topologies based on fixed speed diesel generators and variable speed wind turbine coupled to doubly fed induction. So you see diesel generator using squirrel cage induction generator, diesel generator using PMSG, diesel generator using synchronous reluctance machine, diesel generator using classical synchronous generators, and here you can see this is the wind turbine defig machine. On the rotor side you have AC to DC converter, and then this is a DC bus. See, this is the AC bus and this is the DC bus. On the DC bus you have battery bank, maybe a dump load and a capacitor, and here you have DC to AC converter. So fixed voltage and frequency you connect it to the AC bus. So the power flowing from stator to this, or it can go through this also. Here you have a battery bank and the dump load. Again, topologies based on fixed speed diesel generator, variable speed wind turbine coupled to squirrel cage induction generator. So diesel generators, see different type of machines you can use, and with the wind turbine you can use squirrel cage induction generator, and then here you need full size back to back converter, while in defig you have 1/3 size of this thing. Okay, but with squirrel cage, because on rotor side there is no winding, right? So on stator only you can connect back to back full size converters, and this is the DC bus where you have battery bank and dump load, etc. Topologies based on fixed speed diesel generator, variable speed wind turbine coupled to synchronous generator. So see different types of machine used with diesel generators, and here you have a wind turbine and classical synchronous generator with automatic voltage regulator and exciter. Okay, and the stator is connected to the full size back to back converters. Okay, so this may cost a little bit more. First of all, this machine is costly, and then you have full size back to back converter, and this is the DC bus where you are putting battery bank and the dump load. Topologies based on fixed speed diesel generator, variable speed wind turbine coupled to PMSG. So you see diesel generator connected to different machines as a generator connected to the AC bus. You will have constant voltage and frequency here. But if you see this wind turbine, this is PMSG, and stator is connected to the full size back to back converters. So this is a little bit costly thing. Topology is based on fixed speed diesel generator, variable speed wind turbine coupled to synchronous reluctance generator. So you can see different types of machines are here for diesel generator, but within wind turbine you have synchronous reluctance generator, which is like squirrel cage induction generator, but it is more efficient, considered to be more efficient and robust. So in the stator you have full size back-to-back converters here. Topology is based on variable speed diesel generator, see, and variable speed wind turbine coupled to diffig. Now you have diesel generator with different kinds of machine, but for example, this is diffig, wind turbine and double-fed induction generator. Rotor side, you have 1/3 capacity of this converter, AC to DC converter. This is DC bus. And on this DC bus, you are bringing your diesel generator output. So this is producing AC, but you have AC to DC converter. You are bringing this voltage power on the DC bus of this. So the power will flow like this to the AC bus. So it means the size of this inverter will increase because it has to take care of the power coming from diesel generator also. But still it is very efficient because it is a variable speed diesel generator. Okay, so if the load is less, you can have a less speed, but the efficiency of diesel generator will be more. Okay, and you see a very interesting topology here. I think it was developed in Peru. So diesel engine with doubly fed induction generator. Stator is directly connected to the AC bus, and rotor side you have AC to DC converter, and which is coming to the DC bus, and this is again doubly fed induction generator for wind turbine. Stator is directly connected to the AC bus. Rotor side you have AC to DC converter with 1/3 capacity, but the size of this inverter will increase because power has to flow like this. Okay. Topology is based on fixed speed diesel generator, variable speed wind turbine coupled to diffig and solar PV array. So you see, this is wind turbine, doubly fed induction generator. Rotor side you have AC to DC converter of 1/3 capacity. Then this is the DC bus where you have battery bank and dump load, and then the size of this inverter will increase because PV power is also coming on DC. So this power will be transferred here. So PV power, this is DC to DC converter for MPPT, and this power is coming to the DC bus. So size of this inverter will increase because this power plus this power is going, and this is fixed speed diesel generators. Topology is based on variable speed diesel generator, variable speed wind turbine coupled to diffig and solar. So you see, again suppose we say wind turbine, the fed induction generator, rotor side, 1/3 capacity, AC to DC converter, but then on this DC bus, diesel engine output is coming, and also PV output is coming on the DC bus. So the size of this inverter will increase to take care of this power and this power also. Okay, so you are having variable speed diesel generator here. And again the same thing, suppose you have diffig machine here for wind turbine, rotor side 1/3 capacity, AC to DC converter, but diesel engine you are having doubly fed induction generator, stator is connected here, and rotor size 1/3 capacity, but this power is coming to the DC bus. Moreover, power from PV is also coming to the DC bus. The size of this inverter will increase. hybrid wind diesel PV fuel cell system based on variable speed generator. Okay, so you see this is AC bus, this is DC bus, and on the DC bus you have here DFIG, here PMSG, here synchronous generator, here PM build DC, squirrel cage induction generator, synchronous reluctance generator. So this DFIG rotor is connected to this 1/3 capacity of this machine. Then you have a fuel cell system also on the DC bus. This is DC bus and this is AC bus. So fuel cell is connected to the DC bus, battery bank is there, and then PV is also connected to the DC bus, and diesel generator using this machine is connected to the DC bus. So this is the interphasing inverter between DC and AC bus, and power can flow either in this direction or in this direction. And this is hybrid wind diesel PV fuel cell micro hydro system. So here you have added a micro hydro. Sometimes what happens, there is a small community, and in the back of a small community there is a small river going, because generally what happens even in India, in Canada also it is like this, that those communities are generally near a small river, right, so that you don't have a water problem. So in the north of Canada also there are so many communities just near a small river, although that river freezes during the winter time, but still maybe 1 feet or 2 feet frozen, but under it the water is still flowing. Okay, so you can still use the this micro hydro turbine. Okay, so that's why micro hydro turbine is there. Otherwise rest of the things are same. This is wind turbine with W-fed induction generator, rotor connected to this AC to DC converter. This is the DC bus, this is the AC bus, and then fuel cell and battery bank and PV and variable speed diesel generator. But these are different machines, so little difference in topologies. So coming to the conclusion, electric power supply to many isolated regions of north of Canada is presently being managed by diesel generators. You cannot avoid the diesel generators. Efforts are being made to integrate renewable energy sources to reduce fuel consumption. Otherwise, the cost is very high, like I told you, 43 cents or 90 cents per kilowatt hour. Standalone wind energy conversion system with battery are suitable alternative for small and medium power demand. To increase the efficiency of diesel engines, variable speed diesel engines are now available in the market. But further research work is being done to promote various high efficiency topologies of electrical generator. Researchers are attempting around the world to develop cheaper, lightweight, more efficient electrical machines. As I told you, synchronous reluctance machine, and still work is going on to improve the efficiency and the performance, and to reduce the dependence on permanent magnet, because 90% of the market of permanent magnet is occupied by China. So you are depending on basically on China. In future, with the development of proper technology, DC microgrid may be a more logical solution. And in the next lecture, I will tell you, because so much work is going on data centers. Data centers is the thing of the future, and still now in India also at many places, they are installing big size data centers, and they consume lot of power. And this is what the topic of discussion I attended in July this year, 2025, PES general meeting in Austin. And the first day panel session was on this thing, that the 4 CEOs of the big companies, they were discussing about this thing, that data center will consume lot of energy, we need lot of energy for data centers. Many combinations of hybrid renewable energy systems are being researched, developed with promising results. Depending on the availability of natural resources, and the budget. So if you don't have budget, you cannot do anything. You can have big plans, but you don't have money. What will you do? Moreover, you have to see what are the natural resources available nearby. Like in India, situation is different. North of Canada situation is different. Temperature is different. In India, all the time you have good weather. In Canada, everything freezes in the winter. US, there is a situation different. China, there is a different. So different type of batteries, perhaps. Whatever batteries you are, lead acid batteries you are using, perhaps during the winter time in Canada, you cannot use those batteries. Otherwise, you have to have a heated room for the batteries. So there are so many factors. Every part of the world, they have different solar radiations, wind profile. So depending on that solar radiation and wind profile, your topology will change, right? So you have to see how much wind is there in particular region, how much solar irradiations are there. So the topology will change based on this thing. So as Professor Madhusudan Singh has entered here, so I am finishing my lecture now. Thank you very much. So this is a tea time now. Yeah, yeah.
We can go for tea. Now they are mostly in examination mode.
Yeah.
So they are trying to look back what was done for last 5 days.
So Professor Madhusudan Singh, I just discussed different topologies here. यहाँ पे hybrid standalone, they are not connected to the grid. Hybrid standalone renewable energy system. So I discussed many topologies here. So just to give the basic idea of what is going on around the world, and I discussed.
In Canada, what is the wind speed, average wind speed?
Yeah, so this is what I discussed, and maybe I will give you the brief idea in my next lecture also. See, this is the wind profile. Average wind profile in Canada. In the north of Canada, lot of wind. So if you see average wind power, so in this region, you have around 1000 watt per meter square of power generation in Canada. And even other part of the world, 500, 600 watt per meter square of power generation due to the wind.
Quebec area, it is,
Yeah, this is the Quebec area. So in the Quebec area, in the north of Quebec, it is very good. North of Quebec, it is 500, 600 watt per meter square. But,
it comes in north, sir,
pardon? No, in the south. All big cities in Canada, in the south of Canada, near the US border. Like Vancouver, Montreal, Toronto, they are just near to the US border in the south. So most of the population in Canada.
So we have, I think one more lecture is left.
Yeah, see, this is the south of Canada. So all the grids are there. But in the north of Canada, there are so many communities which are not connected to the grid. So this is what I was talking about this. They need diesel generators. They cannot avoid the use of diesel generator. So a lot of work is going on to integrate renewable energy with diesel generators to reduce the overall cost of the diesel generator. Otherwise, it is very costly. So I told that I am in Montreal. My cost of electricity, I pay to Hydro-Quebec 7 cents, 8 cents per kilowatt hour. But in the north communities, it costs 42, north of Quebec, 42, 43 cents per kilowatt hour. And in other part of Canada, it may reach even 90 cents per kilowatt hour. So this is very costly. But
Hydropower in Quebec, that's why it is cheaper?
yeah. So we have 100% renewable energy, non-polluting power in Quebec. 90% is hydropower, around 40,000 megawatt. And 4,000 megawatt of wind energy in Quebec. But we don't have much solar. And I told yesterday, I was telling a very good, interesting story about solar, that I wanted to install solar panel at the roof of my house. And then I came to know that I will not be able to recover my money for next 28 years. Because the electricity is so cheap in Quebec, you cannot recover your money. While in other places in California and New Jersey, the price of electricity is high, so it is faster to buy. Some people were saying in 2-3 years, right? You were telling that in Rajasthan you are able to recover your money in 2-3 years. So, but this is not the case in
India. It is now business. In fact, there are many remote villages.
Yeah.
Where farmers don't want to do farming, rather they want to do this solar business. They are allowing companies to install,
Yeah.
and they are paying monthly around 1 lakh, 2 lakh to them, and they are
Yeah.
happy with that, no farming required.
Yeah. Yeah.
Especially area where the cultivation was not good, agriculture lands were not good.
But I thought in India everything is connected with the grid now. Mostly connected, right? Yeah. So there are many very small places.
Rooftop which government is installing all over the country.
Yeah.
Under a government scheme of Prime Minister Saur Urja.
Yeah.
That is all great. I think that we can break for tea and then we can again.
And another lecture, don't go anywhere. Another lecture is equally interesting. The next lecture.
Unfortunately, I had some
Okay.
official engagement studies. So
Yeah, no problem.
please join for the tea and then come back. We'll have the last
Yeah.
lecture.
Yeah, 1 minute.
Followed by that, we'll have a
ये लगा रहे हैं हम.
सर बस माइक ऑफ कर देता हूँ
ठीक है.
सर माइक ऑफ कर दूँ या
हाँ कर दो मेरे को तो जाना है. निकाल लो सर. टेक आउट.
ओके सर
ग्रेड सीट का फायदा ये है कि आप अपना क्रेडिट एबीसी जानते हैं, इकोनॉमिक बैंक ऑफ क्रेडिट गवर्नमेंट ऑफ इंडिया ने बनाया, आपका क्रेडिट उसमें अपलोड करेगा।
यस सर
हमारा
हाँ सर मैं सब लेक्चर करता हूँ
इसे बंदी कर ठीक है. Okay. Okay, so now this is the final lecture of my presentation. I want to thank DTU for giving me this opportunity. Professor Madhusudan and everybody are so helpful. Thank you very much, everybody. And especially I find so nice that you have such a nice faculty. Everybody are sitting there talking informally. I really find it very interesting. Thank you very much for letting me know this thing. Okay, so in this lecture, I thought it is good idea to give some what is this situation, electrical energy situation and microgrid projects in Canada. So in this presentation, I will give power sector overview in Canada, then independent electricity system operator. They have some forecast for Canada, then installed wind and solar capacities in Canada, although we discussed a little bit in my earlier lecture, then wind profile in Canada, solar profile radiations, this we have already discussed, and then Canada diesel dependent communities, clean energy for rural and remote communities program has been started by Government of Canada a few years back, then microgrid solution, climate change situation in Canada, some supported grid connected and off-grid micro projects. I will give you some idea, and then we did some projects. I will discuss about those things. So as you can see here, %79% of Canada's electricity is generated from non-polluting sources. 79%. How those 79? 55% is hydropower, 15% is nuclear power, so 70%, and then 9% is solar and wind power. So this is how 79% is from non-polluting sources. Then we have fossil fuel, 21%. So you see here in this diagram, this is 55% hydro energy, then 9% is wind and solar, then nuclear energy, then the Canada power sector review, and if you see total terawatt hour, it is around 630 terawatt hour of total power, and then emission from sources, polluting gases, they are slowly being reduced from to generate the electricity. So if you see Canada independent electricity system operator electricity demand forecast. So see, if you see the industrial sector, it's around 42 terawatt hour of industrial sector electricity demand presently, and in next 25 years it will be around 70 terawatt hour. So this is how it will increase in the next 25 years. If you see the commercial sector, it's also around 42, 43 terawatt hour, and the next 25 years it will be also around 70 terawatt hour. Residential sector, as the population is slowly increasing, so the residential demand will also slowly increase. Then the transportation sector. See, presently we have around 1 or 2 terawatt hour in transportation sector, but in next 25 years, it may reach around 45 terawatt hour because of electric vehicles and those things, right? Because big work is going on in this direction. Then the data centers, presently it is around 1 or 2 terawatt hour, but in the next 25 years, it may be around 15 terawatt hour. So this is what I was telling earlier in the earlier lecture, that data center is a big power consumptions, and I was there in Austin PES general meeting in July 2025, and the opening panel session discussion, there were 4 CEOs of big companies, and everybody was emphasizing on this thing that data center will be a very big consumption. They will need a lot of consumption of electricity. It is only in Canada that from 1 or 2 terawatt hour, it will go to is born. So this is the population situation. Everywhere in India, New Canada is born. So you cannot compare the two things, right? So this is what it is. But if you see from other point of view, as I always telling, that in my province, home province, Quebec, we have 100% electricity, renewable energy. While in India also a lot of work is going on, like how much, around 75 gigawatt perhaps wind, and then more than 130 gigawatt of solar or something. So a lot of work, so much work, incentives given by the government, a lot of work is going on in India. So this is what is the situation in Canada. So Canada, 79% is non-polluting sources. I think we have around 150,000 megawatt of power generation total in Canada, out of which around 79% is non-polluting. While in India, how much? 450,000 gigawatts, no, 450,000 megawatt or something. And around 55% I think is renewable presently. This is the situation in India.
Canada installed capacity is 150 gigawatt.
Yeah, something 145,000 megawatt to 150,000 megawatt, something like that. 145 gigawatt to 150 gigawatt, something. But in
around, I think, 485 gigawatt.
Yeah, 485 gigawatt in India. And I think around 50% is renewable energy.
In India, we do not have 50%. I think
Yeah.
30%.
How much?
20 to 30%.
No. You have, I think, more than 200 gigawatt is renewable energy. Wind is more than 75,000 megawatt, 75 gigawatt, and solar is also around 130 gigawatt. So more than 200 gigawatt in India you have renewable, out of 485 you are saying. But I saw somewhere that is around 51% in India is renewable energy now perhaps. Because then you have nuclear also, and perhaps that's how perhaps they are calculating. Okay, so this is, we have already seen the wind profile in Canada. North of Canada, wind profile is fairly good, and the power generation we have already discussed in my last lecture. And solar radiations also we have already seen in the south of Canada. We have very good potential of solar energy, more than 1,500 kilowatt hour per kilowatt of installation per year. So this is how we define. And in this is the province of Quebec. In Quebec also, South Quebec, you see very good potential. Even in the north of Quebec and the north of Canada, it is not that bad. You have around more than 1,000 kilowatt hour per kilowatt of potential. So this is what we were talking about, Canada diesel dependent communities. So this is what it is about, the diesel dependent communities. So in the north of Canada, you can see all those communities, they are totally dependent on diesel. They are not connected to the grid. In the south part, almost it is connected to the grid. But there are 250 communities in total in Canada which are not connected to the grid. So they are totally 100% dependent on diesel generators. So this is the situation, and as I have told you, this it is very costly, diesel consumption, diesel cost. As I told you, in Montreal I am paying 7 cents, 8 cents per kilowatt hour, but in the north some communities are paying 43 cents per kilowatt hour. In other part of Canada, even 90 cents per kilowatt hour electricity cost is there, because the diesel has to be airlifted in many communities. So you see in this table, perhaps you cannot see, it is very small, but there are some communities, the diesel has to be airlifted. So that is why cost is high there for diesel, right? Long distance barge is like a big boat, flat bottom boat you can see. So they transport many times diesel through this. So that's why bulk price of diesel fuel in some communities $2.36 per liter. So this is very costly. In some other communities, like see, sometime winter roads are there. Winter roads means lake is there or river is there. In winter time it freezes, so you can drive on the lake or river, so you can deliver. Otherwise there are not proper roads there to deliver to those communities. Yeah, winter road. Winter road is the same thing, like there's a lake which is frozen, and then you drive maybe 1 feet or 2 feet of solid ice, and there you can drive your car or truck on that road. Although it is risky, but it is done. It is the normal way during winter time. Then you see some are highway connected, so it is cheaper there. Greenhouse gas emissions for electricity, you see, this is for different, like transport, and this is transport thing, orange, and then green for electricity. So for generation of electricity, slowly the consumption of diesel is reducing, and you see the greenhouse gas emission for generating the electricity is becoming less and less. Now, since we are talking about remote communities, for electricity and heat generation, this is for electricity generation for remote communities, 79% is dependent on diesel, 19% solar, wind, hydro, those things, and then other fossil fuel like gas and coal and those things. So this is for electricity generation. Now for heat generation also, 69% are dependent on diesel, 10% other fossil fuel, and wood stove 20%, and biomass, and that is only 1%. So this is the situation. Now the efforts are being made to reduce the diesel consumption. Okay, and there are 4 pathways through which the diesel is used less and less. So one is energy efficiency, another is renewable electricity, renewable heat, and grid connection. So these are 4 ways how the diesel is less and used. Pathways to diesel reduction in remote communities. Diesel equivalent use, suppose in 2015 this much diesel equivalent was used, but over the years it is being reduced because of these 4: energy efficiency, because energy efficiency of like generators or machines or equipment. So government is emphasizing if you have a better efficiency, then there will be less consumption. and then renewable energy, these things are there. So in 2020, 4 pathways collectively contributed to 12.3 million liters of diesel equivalent fuel that is not burned. So 2020 year, in 1 year, 12.3 million liters of diesel equivalent fuel was saved, it was not burned. So if you see here, even with this cumulative annual reduction in diesel equivalent fuel, the estimated annual diesel equivalent fuel required in remote communities, 682 million liters per year, is still used in remote communities, the diesel, to generate heat, to generate electricity and those things. Out of 682 million liters per year, 221 million liters per year for electricity and 461 million liters per year for the heat. Okay, this is annually. So energy efficiency, it caused 1.1 million liter per year diesel equivalent consumption reduction because of the energy efficiency. Because of the renewable electricity, 3.5 million liters was saved. Because renewable heat, 4.1 million liters per year was saved. Grid connection saved 3.6 million liter per year. So total 12.3 million liter equivalent diesel was not burned because of these 4 pathways. Now, what is the objective for from 2030? See, in 2020, what is there? In 2020 is there 682 million liters of diesel used, out of which 221 million for electricity and 461 liter for heat. So presently in 2020, this is the situation, 682 million. So in 2030, what Canadian government wants is to eliminate diesel power electricity generation by 2030. They don't want diesel power generated electricity. So it means you will be able to save 220 million liters per year by 2030. And by 2050, even that will also be not use this heat generation. So by 2050, for remote communities, no diesel should be used to generate electricity or to generate heat. This is what is, so this is what is global net zero we are talking about in those COP 26 or COP 30 conferences, that reduction of use of diesel, and by mid-century, by 2050, we should have global net zero. This is what we are talking about. Although, as I was telling you yesterday, that when I visited China, China's objective initially was also 2050 for having global net zero. But after discussion, as I told you yesterday, that they are having the major problem, China is having a major problem for voltage instability in the grid. And that voltage instability in the grid is caused by too much renewable energy sources. In China right now, I think it is 79% of energy is coming from renewable energy sources. Only in 2024, whatever power generation they added on the grid, 86% was renewable energy in China, 2024. So much renewable energy they are integrating in the grid. And that is causing the problem of the voltage instability on the grid. So I was talking to engineers in some universities, and especially China Energy. There is a very big lab where Professor Hua Gang, he is a professor at Tsinghua University, and now he has second post in China Energy. There's a big research center they have opened, and presently 50 PhDs are working under Professor Huageng. Professor Huageng is a very good friend of mine, and he is saying that next 4 or 5 months, he will engage another 30 PhD people, researchers in his group. And what is the objective? To study about the voltage instability on the grid. And so I was discussing with many engineers and their chief. We had a discussion on the round table, and they were saying that initial objective of China was to have global net zero by 2050, but now because of the voltage instability, they have shifted it to 2060. And why? It is because of the voltage instability. Too much renewable energy is there, and that is causing the problem. So by 2030, till 2030, they will be adding thermal power plants. This is that's why till 2030, they will be adding more thermal power plants to make the grid more stable. So from 2050, they don't have any choice, they have to shift it to 2060. And because of the voltage instability, they are doing lot of curtailment of renewable energy integration. So there was a conference, I was a panelist in the conference organized by that company, automotive company, and Professor C.Y. Chung, he is the new president of IEEE PES society, and he's a very good friend of mine. He invited me to Hong Kong to give a lecture, and he was also panelist. I was also panelist in that conference, one-day conference organized, and I gave my presentation, and there were 2-3 researchers from State Grid Company of China. So those two people, C.Y. Chung was giving presentation, and you know what he was talking about? He was talking about how to reduce the curtailment of renewable energy. How to reduce the curtailment of renewable energy integration in the grid. He was presenting, and that company was pushing for more battery energy storage. So we were discussing there. So I said that, okay, we have, if you want energy storage on large scale, we are not talking about a small scale, we are talking about energy storage at large scale. So large scale energy storage, you know the pumping stations, you have reservoir, you pump the water back to the reservoir, right? Pump storage power plants we have, and then some researchers in California and other places, they are suggesting that we should store hydrogen in mine sites, like they have basalt rocks and underground, 1 kilometer deep underground, you have basalt rocks and other rocks. There you can store hydrogen. But then we were saying, okay, hydrogen is not that safe. You are talking about lithium battery, which is exploding, and then you are talking about hydrogen storage. Hydrogen may also explode. So this is what they were saying. The company was pushing for vanadium redox battery. Then I told, okay, vanadium redox battery has less power density and it is big size, but the advantage is that it has a less leakage of charge. Yeah, it retains the charge. So this is what they are pushing, vanadium redox battery at large scale. So they were suggesting every city should have vanadium redox batteries at large scale underground, and they should store the energy in that, and then when the voltage instability comes, they should inject that battery storage power to the grid instead of curtailing the renewable energy. So Professor Chung was showing how much less curtailment of renewable energy we can have. So now see, this is the problem in China. They are talking, they are already doing the curtailment of renewable energy. Okay, they are already to make the grid stable. That is the big problem, making the grid voltage stable. So they are doing curtailment of renewable energy. And yesterday I was talking about there's a big wind energy farm, Gansu Park, where they were supposed to have 20 gigawatt of wind power, but instead of 20 gigawatt, now they are having only say 7 or 8 gigawatt, although this is the largest wind farm in the world. So they are doing curtailment there, and they are not pushing to put more wind turbines there because there's a transmission problem. They have HVDC line because it is far away, and there is a management problem. So a lot of problem in renewable energy, although every year they are putting more and more solar and wind, but now they are going for curtailment of. So this is what actually the problem. So India also has to be very careful about putting more and more renewable energy. They should try, but I think we are doing good here, because you are at the same time, I think new nuclear plants are also coming into picture, right? So this is a very good step. China is going for thermal plant, so perhaps a nuclear plant also, but coal plant also, but India is going for nuclear plant, but India should not go for coal power plants. That is not a right step to go, because someone at NTPC was talking about making this 1200 megawatt of turbine, thermal turbine, all those things. I think that may not be a good step. But anyway, this is not my concern, but this is the thing that in Canada, by 2050, we want to be this thing. Okay, so coming to this topic, some supported microgrid projects in Canada. So there's a program, Green Infrastructure Smart Grid Program by Government of Canada. They have started in 2018. So the Smart Grid program invests $100 million over 5 years in this program. So it is started in 2018. So first batch, 5 years, they invested $100 million, but then in 2023, they again renewed it for another 5 years, $100 million over 5 years. Green microgrid projects, okay. So there are so many microgrid projects everywhere going on. Some projects are demonstration projects, some are deployment projects, some are hybrid projects supported by Government of Canada, and total there are 22 projects right now which is going on. So this is the list of 22 projects, but I will not go in the list of this thing. But one interesting project is Lac Mégantic Microgrid Canada. So what happened in 2013? One train was coming from Western Canada, bringing the crude oil from Alberta. It crossed Ontario and then it came to Quebec. And this train was full of crude oil. All the wagons were full of crude oil. So driver was feeling sleepy. He stopped the train just before one town, Lac Mégantic. Lac Mégantic is the name of a town. He stopped there, the train, put it on brakes, but engine was still running, and he said, okay, I will take few hours of sleep. So he went somewhere to take a nap. And then somehow the brakes failed of the train. And train started moving and it picked the speed, and right in the middle of downtown, it crashed. All the crude oil, the total downtown area was burned down in that town. 47 people died in 2013. So this is what happened. So this was a very serious matter. So after that, government said, okay, we will renew the town. So they invested money, and you see the whole, they had microgrid there, they have 800 kilowatt, 800 kilowatt of 2,200 solar panels, 700 kilowatt hour of battery storage, EV charging station, all those things are there in this town now. Now it is functional. So in this town you can see this is the photovoltaic energy month-wise for the whole year. So during the summer time there is enough solar power which can supply the whole town, while during the winter energy consumption because of the heating and those things is more, so you cannot, so during this time because it is grid connected, okay, this is the grid connected project, so power comes from the grid. Another project, Sleman Park microgrid project, Prince Edward Island, it will offset 4,500 tons carbon dioxide emission per year. So it will have 10 megawatt of solar farm. I think it is still not functional. It will be by 2030. 1.5 megawatt hour lithium ion battery storage system. Objective net zero energy by 2030. So you see 10 megawatt hour solar farm, battery energy storage, everything is there in there. So this is underway. Then secondary school carbon-free embedded microgrid project in the town of London. Okay, so they have this geothermal heating and cooling, 50,000 feet of drilled pipe. They have 100 feet by 500 feet. And then 2,300 solar panels of 804 kilowatt hour DC power, and then 1.1 megawatt power thermal and solar, 2.2 megawatt hour energy, electrical energy storage system, and those things. So these projects are all supported by the government. Then they have Arriviat Clean Energy, Nunavut, there is a small town, over 20 years will reduce diesel use by 30 million liters. So they have 200 kilowatt solar, wind 1.6 megawatt, battery 2 megawatt hour. So this is the thing. And then there is another microgrid project which will save 127,000 liters of diesel each year. It opened in 2025. Okay, so these things are there. Glencore, this is the mine, nickel copper mine. Okay, now phase 2. So this is already there. 3 megawatt of Enercon wind turbine, flywheel. So you see, this thing is already installed. But now phase 2 again they are putting 3 megawatt of wind turbine. Then there is a Technosant Aeolian Energica. This is experimental, this is hybrid type of project. So there are so many things, so I will not go in much detail of this. Very interesting thing is that few years back we did a very interesting project for a iron ore mine in the north of Canada, in the province of Newfoundland and Labrador. So this mine site was using 150 kilowatt of diesel generator to provide some electricity to the locals, and then there was a community center. So the engineers and management was not satisfied with that diesel generator because it was making lot of noise, pollution, fuel consumption, maintenance, operational problems. So they wanted to reduce the fuel consumption and those things. So we asked them to provide the data, what is the load, okay. So you see this, you will be it's very interesting, load power demand, month-wise, January, February, March, April, starting from December, load is less than 10 kilowatt, and they were using 150 kilowatt diesel generator. It is because during the winter it is very cold, minus 40 degrees centigrade temperature, nobody is working in the mines in that cold. So only the community center was running and perhaps no one was there, so that's why it was very less power demand there. Then in the month of May, the workers returned, so still it is less than 30 kilowatt. And then June, July, August, temperatures are good, so consumption is reduced. Then September, October and November, that is the maximum consumption maximum load was 40 kilowatt. And they were using 150 kilowatt of diesel engine. So that was the problem. So we asked them to provide us solar and wind data. So this is what they provided. Blue is the solar radiation during the summer time. Solar is very good, but during the winter time it is less. But if you see the wind, during the winter time wind is very good, although summer time it is less. So it is very good complementary thing. So it was a good sign. So this is what they said. So the objective was the integration of renewable energy sources available locally in Esker mine site with existing diesel generator. They still wanted to use the same diesel generator, but they wanted to integrate renewable energy sources to reduce the overall consumption of diesel. To propose new configuration which is able to operate with low wind speed and under severe climatic condition to ensure clean, stable, uninterrupted power supply to connected load. So this was the objective. So there were three configuration we discussed. First configuration was they can still use 150 kilowatt diesel generator, but since the maximum load was 40 kilowatt, so we told them, okay, you can put one wind turbine of 40 kilowatt. But they said, no, we don't have equipment to put 40 kilowatt, it will be long tower. So they said, okay, we can put 10 kilowatt wind turbine, 4 wind turbine of 10 kilowatt. So they have the equipment to install it. So we said, okay. Then the 4 solar panels of 5 kilowatt each to give total 20 kilowatt from that. And then power electronics related with this, you have AC to DC converter, DC to DC converter. This is the DC bus. Okay, so this is for solar, this is for wind, and then there was a battery bank. Okay, and this is the AC bus because of your diesel generator, and between AC bus and DC bus there was a bi-directional converter here. The power can flow either in this direction or in this. So this is the first topology we discussed. In another topology, we visited their storage facility and we found they already have 2 diesel generators of 27 kilowatt each. So we told them that is a very good thing. You already have 27 kilowatt, 2 diesel generator, which perfectly fits. So this is what this diesel generator 27 kilowatt, another diesel generator 27 kilowatt in parallel, and then the same structure, 4 wind turbines of 10 kilowatt each and 4 PV panels of 5 kilowatt each with the same architecture, and one engineer used the compressed air technology to improve the efficiency of diesel engine, so he suggested this. But finally we agreed to this topology that we should use battery bank and keeping the same structure, 2 diesel generator of 27 kilowatt. So this is, and then bi-directional converter. So everybody agreed that okay, we should do a study on this. So I engaged one postdoc, one PhD student to do a study, do simulation work and those things. So this is for MPPT of wind turbine, MPPT of solar panels, and then this was the control algorithm for bi-directional converter. This, although it looks complicated, but it is not that complicated, because you see this is for phase A and similar for phase B and phase C. Okay, so here for phase A, for example, you are measuring phase A load current, then voltage in phase and voltage in quadrature. Okay, and then finally you are calculating in-phase component of load current and quadrature component of load current. Then for phase A, phase B and phase C, then taking average, and you are calculating in-phase component of load current. And similarly you are calculating the quadrature component of the load current, and where you are adding for voltage regulation things, right? So load side reference voltage and actual voltage measured. So this will give the quadrature component for voltage regulation, and here from the battery backup the reference is coming here. So this is how finally the students and postdoc they generated. Another thing was the control strategy for the diesel generator. So this is diesel generator 1, this is diesel generator 2. When you are going to connect the diesel generator 1? When the state of charge of battery less than 50% and the load power is more than PV power and wind power. And then you know both sides, you have to see voltage amplitude, sequence, right, and the phase angle. Then you connect this switch. Okay. And when you are going to connect the second diesel generator, their state of charge of battery is less than 50% and the load is more than diesel generator 1 plus PV plus wind turbine. Then only you close the another switch. Then the student did MPPT for all PVs and wind turbines, and then simulation studies of all these things. I will not go in detail of this thing. And this is interesting result. If state of charge of battery is 100%, what will you do at that time? So load was, for example, 20 kilowatt and PV and wind power is 30 kilowatt. It means the rest of the power was going to the battery here. But at this point battery is fully charged, so you cannot put more power to the battery. So you have to start the dump load. Dump load may be pumping the water perhaps in the tank, or you may heat up the room, right, community hall and those things. So at this point you are switching on the dump load, so extra power which is generated by renewable energy sources is going to the dump load. Okay, so load is here which is stable 20 kilowatt, but at this point load is increased to 50 kilowatt from 20 kilowatt. So, but the wind and PV was providing 30 kilowatt, so 20 kilowatt power will come from the battery. So battery is on now, and you shut off the dump load. You shut off dump load, switch on to battery, and so battery is providing the extra power. Then we started, suppose this is the load current and PV and wind turbine current is this one. Perhaps that is not sufficient, so you have to synchronize diesel generator 1 and you can connect diesel generator 1. But at this point load is increased, so you had to synchronize diesel generator 2 and you are connecting the diesel generator 2. So all these studies were done by the student, and to make sure that diesel generator 1 current and diesel generator 2 current, they are sinusoidal constant current even though the load is highly nonlinear. So the inverter currents, they are taking care of the harmonics and everything, so that the diesel generator 1 and diesel generator 2 currents are not distorted much, and the load voltage is constant sinusoidal. Then we did the real laboratory implementation with PV, and this was actually a project of another company, Emalog, which cleaned the water, but that company Emalog has been bought by Swiss, Canada, another company, and now a third company has taken over that company, Veolia. So this was done with Emalog, that they had ozone generator and they wanted some centrifugal pump, so only with PV power, so we did, and with that we did the implementation for our mine project also. Okay, first we are using PV here. Then, so this is the experimental setup we did, and then we added the diesel generator in this. Here we did test, and then we added wind turbine also. So this is basically one set of test we did after simulation. We did hardware implementation in the lab, those things. Then there are some other projects going on. I will not go in detail. Okay. So coming to the conclusion, electrical energy situation in Canada in general is reasonably good, with around 79% coming from non-polluting renewable sources. Electric power supplied to many isolated regions of north of Canada is presently being managed by diesel generators. Efforts are being made to integrate renewable energy sources to reduce the fuel consumption, cost, air pollution, etc. Some government-supported grid-connected and off-grid projects were discussed. Performance of the proposed solution, so we find it very interesting and we suggested it to the thing. Thank you very much. If you have any question, please, you can go ahead. No question is fine, but we can have some informal discussion if you want to give your input and those things. That is okay if there is no question.
They are worried about their exam.
Oh, okay. Now they have a test.
After 10 minutes.
Yeah, test is very important.
So let us give a big round of applause to Professor Chandra.
Thank you. Thank you.
Sir has very nicely finished the 14-hour capsule of power quality. This was the last session, and we have scheduled a small exam. Followed by that, we'll have a valedictory session. And my request to all of you: write your exam seriously, try to do your best, and then please reassemble timely so that after lunch, I hope your valedictory will be after lunch. So after lunch we will reassemble and finally close this 5 days program. So thank you all for attending this program, and I especially thank Professor Chandra for taking a lot of pain to deliver this 14-hour power quality lecture series. I am also thankful and happy to share with you all that Professor Anjali ma'am is here, the wife of Professor Chandra, a graduate of Delhi College of Engineering, 83 batch, graduate of Electronics and Communication, and she is presently the professor at University of Concordia, Montreal, Canada, and the brother of Madam also, Mr. Raj.
Is the graduate of Delhi College of Engineering.
Also a graduate of Delhi College of Engineering and has served the NTPC for a long time. Now he is recently superannuated and enjoying the retirement.
And his son is also graduate of Delhi College of Engineering.
And his son, Mr. Neeraj, was also a student of Electrical Engineering, Delhi College of Engineering. I taught him, I think.
Yeah,
So,
25 years ago.
So the entire family has a very strong affiliation to this institute, and that we all feel proud of all of them, that they were associated with this prestigious institute. So thank you, sir, for coming, and let us formally close this session, sir. Now we'll go for tea and lunch. They will go for exam, I hope, and then after lunch we'll reassemble. We'll have a valedictory session, formally a closing session. So thank you all.
Thank you very much, everybody, for everything. Thank you.
क्या सिस्टम दिखाया
ठीक है। A very good evening to everyone. I am Arpana Singh, and it is my honor to welcome you all to this valedictory session of this one-week short-term course on recent advancement in power quality-based controllers with grid integration of renewable energy sources, design, mitigation techniques, and the performance analysis at the distribution level, held from 1st to 5th December 2025. I warmly welcome all the dignitaries, Professor Madhusudan Singh Sir, Director, IIIT Bhagalpur, and Course Coordinator GIAN, Professor Pragati Kumar, Vice Chancellor SMVD Katra, Professor Rachna Garg, Head of Department Electrical Engineering DTU, Professor Amrish Chandra, Resource Person and International Faculty from École de Technologie Supérieure, Montreal, Canada, and I also welcome a very special guest today, Professor Anjali Agarwal, who is an award-winning academic leader and has won Distinguished International Alumni Faculty Award 2025. She has done a PhD in electrical engineering from Concordia University, Canada. She has been widely recognized for her contributions to engineering education and diversity initiatives. As Associate Dean of Student Academic Services at the Gina Cody School of Engineering in Concordia University. She has led many award-winning efforts to enhance undergraduate programs and expanded research opportunities and significantly increased the representation of women in engineering. Her impactful work in protocol design, machine learning-based network, optimization, smart grid, and further distinguish her as an accomplished researcher and celebrated educator. Now, I further request I also welcome Professor Vishal Verma, Sir, Dean of Alumni Affairs, DTU. Now, I request Professor Rachna Garg, ma'am, to present a token of sapling to Professor Anjali Sharma, ma'am. Ma'am, please. Anjali Agarwal, ma'am. Yeah, ma'am. I would request Professor Pragati Kumar, Vice Chancellor, SMVD Katra, to present a token of appreciation, the International Award, to Professor Anjali Agarwal, ma'am, again. Yes, sir. I request both of the sir, Professor Pragati Kumar sir and Professor Vishal Verma sir, to present the Alumni Award to Professor Pragati Agarwal, ma'am. मोड़ के देना, खोल के देना, खोल के देना, खोल के देना. I would request Professor Madhusudan Singh sir to present a token of appreciation of Angavastra from Bhagalpur to Professor Anjali Agarwal. Over the past 5 days, we have an enriching journey filled with insightful lectures, hand-on tutorials, simulation-based learning, and deep discussion on power quality standards. Today, as we come together for the closing ceremony, let us acknowledge the collective effort, curiosity, and the dedication that shaped this successful academic program. It is my privilege now to invite Professor Madhusudan Singh sir, local coordinator of this course, to address the gathering. Just as he set the academic tone during the inaugural briefing, today we look forward again for his reflections on the weak learning outcomes and the importance of power quality research. Sir, please.
So very good afternoon to all of you, the dignitaries in the dais, the international faculty for this GIAN course, Professor Amrish Chandra sir, Madam Anjali Agarwal, our special guest for today's function, and one of our most distinguished alumni of Delhi College of Engineering 1983 batch, my own colleague and special guest for today's function, Professor Pragati Kumar ji, who is the Vice Chancellor of Sri Mata Vaishno Devi University, Katra, my head of department, Professor Rachna Garg, and the local coordinator, GIAN, Professor Vishal Verma, the Dean Alumni Affairs, and I especially requested him for this particular award, which is already awarded by our Alumni Association, but one or other reason, Madam could not be on that day, and we decided to finally award that award today. My other colleagues present here, participants, ladies and gentlemen, my another friend and also alumni of Delhi College of Engineering, Rajiv Agrawal ji, the brother of Madam Chandra. So you will all surprised that Professor Chandra has come to this place, and because of that we are able to connect our so many alumni. one of Madam Chandra, the brother of Madam Chandra, who is also a graduate of this place, and son of Mr. Rajiv Agarwal, Neeraj is also graduate of this place. Perhaps I and Professor Pragati Kumar Rachna all taught him also. So it's a great opportunity and a great occasion for all of us that we could connect to all of you, such a distinguished gathering. We all are here for last 5 days, and you have seen that it is basically a show which was managed by Professor Chandra. We were just the part of that program, managing logistic and all. But the real contribution and the real effort was of Professor Chandra. And I am really grateful to Professor Chandra that even at this age and if having such a tight schedule, he decided to conduct this course for 5 days. And those who attended the course will really appreciate the way he teaches is a good reflection of an excellent teacher. So let us give a big round of applause to especially Professor Chandra for delivering such a nice series of lectures, starting from basic concept of power quality, and you all could have seen he defined power quality in different sense, not from only utility point of view, load point of view, customer point of view, and so many standard definitions, indexes he has defined in the beginning, and thereafter, if you recall, he also discussed few fundamental tools which are required to study power quality, like symmetrical component theory. In fact, long back in my BTech, I studied that, and then when I was attending here, I could really appreciate that what is meaning of the fifth harmonic, seventh harmonic, and under which category of symmetrical component these harmonics falls, whether it is a positive sequence harmonic, negative sequence harmonic, and all. So it was all very interesting. I think Professor Baumik is not here, but he was very happy to see all those lectures. Really, it was a very interesting moment. And thereafter, you see, he discussed all modern power electronic devices and systems which are used for supplementing power qualities issues. So, and lastly, today lecture, especially the last two lectures which were delivered, you will all happy to see a good integration of renewable energy and our into conventional grid issues and challenges, and finally touching to the microgrid. I was happy to see that Canada is a country where almost 80% energy is renewable. Only 20% energy consumption they are managing through coal plant. And sir was very happy to say that even they are targeting that after some time they will not add any thermal power plants. Where the situation is quite reverse in our country, we are still rely more on thermal. I know because I shifted to Bhagalpur 6 months back, and there is one power plant of NTPC, thermal power plant, recently sanctioned for 2,500 megawatt. So, and I know that the related pollution, everything, those areas will obviously face. So our is a different country. In fact, our requirement is different, population density, so many things. But you all know that the trend is that to move as much we can go for renewables. And earlier I remember that there were some paper people used to say that only 43%, 50%, 45% renewable integration is possible for stable operation of grid. If you go more than that, stability issue, etc. becomes more, difficult. But when I came to know that renewable up to 80%, of course that include a major portion of hydroelectric, then it was really a good input for all of us. So that was just one example I cited, but
If you could see the PPT of all 14 lectures, all were equally exciting and very informative. So my sincere appeal to all of you is that please go through those details और उन पीपीटी को बड़ा संभाल के रखिएगा. जब कभी कभी मौका मिले, कभी ऐसा ओकेजन दिखे कि आपको किसी पावर क्वालिटी पे बोलना है, पावर क्वालिटी पे कहीं इंटरव्यू देना, आप जरूर देखिएगा. Will obviously benefit you, all of you. So there are a lot of many things I can share with you, but at this moment, I am really delighted with presence of Madam Agrawal, who in spite of her ill health and also other engagement, decided to come to this place on our invitation. And we all are happy, ma'am, to see you in your own institute, not your old campus, but a new campus. But obviously, we all feel pride of you, entire our alumni community. You are doing so well, and you always keep our head high. So my sincere regard and gratitude to Madam Chandra. I am also thankful to Mr. Rajiv Agrawal ji, who is the key person to connect us, in fact, and very active alumni of our association. So with this, I once again thanks to all of you, especially my head of department, Professor Rachana, who was looking after the entire show for the last 5 days, and she is also the GIAN coordinator. And the most active, what I should say, coordinator come overall organizer, Dr. Ankita. She was the person who is looking for very beginning, in fact. She, in fact, conceptualized that we should prepare a proposal, submit, and she was continuously communicating with Professor Chandra, taking consent, uploading and all. I just advised her that you go like this. So we should really appreciate the effort of Dr. Ankita. And my all colleagues, in fact, many times I saw that here, most of our teachers were attending all these lectures. When I asked some of the teachers, they said, these are good materials, can help me to teach the subject. So that kind of spirit we really appreciate. And I thank you all participants that you attended this course, and now you have become part of the power quality community. Every day the power quality community increasing. You are now a component of that. And with this entire knowledge, you all are having a good understanding in the area of power quality. So with this, once again, I thank you all and wish you all the best.
Thank you so much, sir, for your insightful address. Now, I would like to invite Professor Rachana Garg, ma'am, our respected local coordinator, whose continuous encouragement, academic leadership, and coordination ensured that this course can run smoothly and fruitfully. Ma'am, please.
A very good afternoon to all of you. I think all of you must have enjoyed this course and must have learned a lot from this course. Is it so? So say loudly you had learned a lot from this course. So dignitaries on the dais, first and foremost, the international faculty for this course, Professor Amrish Chandra, and Professor Anjali Agrawal, who is the special invitee for today's program, Professor Pragati Kumar, who is the Vice Chancellor, SMDU University, the coordinator of the course, Professor Madhusudan Sir, Dean Alumni Affairs, Professor Vishal Verma, then other coordinator of the course, Dr. Ankita, other dignitaries, and my esteemed faculty members present here. And again, last but not the least, all the participants who had attended this course. So first and foremost, I would like to give a big clap to all the participants. Please give a clap for yourself. Because you are the ones because of whom this program was a success. Although, if Professor Amrish was not here, then obviously this course won't be that much successful. But again, with the presence of you all, you had made this program a huge success. And this is, in itself is a testimony to the teaching of Professor Amrish Chandra. Since he is such a good researcher, good teacher, that's why you all are here to attend this course. So, with all my humility, I would like to thank Professor Amrish Chandra for delivering the lectures for this 5-day GIAN program at DTU. And with sir, we got connected with Professor Anjali Agrawal and Mr. Rajiv Agrawal and so many other alumni. And so we thank you for this also. And Professor Anjali receiving the Distinguished Alumni Award for International Faculty is also one of the feather in our cap, in the cap of DTU, that she is, as sir has said, she is from Electronics Department of DTU only. And she is one of our own. And she has received this award. Madam, we are really very happy that you had received this award, and we congratulate you from the bottom of our heart for this award. So congratulations, ma'am. And again, as a local coordinator of GIAN, I would like to say that I had said in the inauguration ceremony also, we had submitted 19 proposals, out of which 3 proposals are from Electrical Engineering Department. And I hope if our proposals get accepted, I will again see all of you to DTU and to the Electrical Engineering Department. Now tell me, how many of you had gone through the laboratories of Electrical Department? Have you seen? And so a few hands, I think, who are truly outsiders, they must have seen the laboratories. And I hope you must have seen that we have very good laboratories in DTU, Electrical Department. And since you are either young faculty or PhD scholars, I hope you will learn from our labs and will try to improve the laboratories or expand the laboratories in your own universities, wherever you are working or wherever you are studying. So with this, I would once again like to thank our international faculty, Professor Amrish Chandra, and the coordinators of the course, Professor Madhusudan sir and Dr. Ankita, for organizing such a timely and a very relevant course. And thanks to all the participants. Thank you.
Thank you, ma'am. It is now my honor to invite Professor Amrish Chandra, whose expertise enriched this course immensely. His lectures on advanced power quality controllers, harmonics, and renewable energy integration have been a cornerstone of the learning experience. Just as his inaugural address inspired by the participants, we are delighted to hear his concluding insights again today. Sir, please.
Thank you very much for the invitation. I am so thankful to DTU for giving me this opportunity, and especially to Professor Madhusudan Singh, Professor Ratnagar, Professor or Dr. Ankita Bhatta, and Professor Vishal Verma, and the Honorable Vice Chancellor. So you see, it is so amazing. I had a very nice experience. I never thought that I will have so much hospitality here. So nice of you. I met so many professors of the department. I had a discussion with them, Professor Mukhtar Singh and other professor. So nice meeting. And whenever I go to the head's office, Professor Ratna Garg's office, environment is so nice there all the time, so informal, and the work is done so smoothly. It was really very amazing experience for me, especially I'm coming from Canada. We have close society. We are not that open to each other, and it's very formal type, but here I find so nice everything. And the participants were there. At least they were not asking much question, that is another thing. But it was a very good experience. Although I tried to compress the material in a very short time, I have many things to present. But whatever I present, I hope it will help you people and you will advance your career, and I wish you good luck in your career. Thank you very much for that.
Thank you, sir, for your inspiring words. We will now take a feedback from participants whose engagement and enthusiasm have been the true driving force of this program. Now, I invite the participants to share their reflections. Anyone from the participant?
Good afternoon, everyone, all the dignitaries here and all those who are present here. I'm Sreshta, a PhD scholar coming from Kerala, and this is my very first time attending a GIAN course, and I think it is my truly inspired sessions I have been here. Very well structured, and sessions by Amrish sir was very informative, and I'm working on power quality itself. But my core area is power quality itself, but the thing is I'm working on AI now, applications of AI in power quality now. So it's been 2 years working on AI. So I have been losing a little bit touch in power quality, and now I think again with the touch of that thing. And thank you so much for the classes, and it was a great pleasure to meet Professor Beam Singh sir also. I feel very lucky to meet those dignitaries here also. And yeah, all those theory sections was good, and one feedback which I had to give is that hands-on sessions on MATLAB, if it was a few more classes was there, it would have been much more good. Other than that, it was a very good experience, and I'm looking forward for more such sessions. Thank you, DTU, for giving me such an opportunity. Thank you so much.
Anyone else? Yeah, please.
Good afternoon, everybody. My name is Anjali. I'm coming from IIT Delhi to attend this GIAN course. First of all, I was not decided to come here. Like, I come to know from my friend. So I thought, like, give it a chance. Then I came here and I found out, like, it is very informative, very clear, and very well-structured course. And not only that, like, the way it is delivered, it's so beautiful. And like Professor Amrish Chandra sir is so nice to deliver the course, like the slides they provided, so beautiful. Like when I was attending this course, like few of my doubts got cleared while in duration of that course, and the slides made it more clear. Like the way he taught, it is just like the professor used to teach in their lectures. So I'm quite happy, and it's my fortune to be here, and very thankful to the professor, all the dignitaries, and all the people who make it happen. Thank you so much.
Thank you, participants, for your beautiful feedback. We move on to the distribution of certificates. I now request all the dignitaries on the dais to please come down for distributing the certificates. I request the participants to come one by one to collect the certificate. कौन सी mic on कर रहे हो? हैं?
agriculture.
श्रेष्ठ गोल केजी, श्रेष्ठ मोल को केजी, अंजलि गौतम, सीमा बाई मीना, लौतिका देवी, डॉक्टर बहादुर सिंह पाली, पुनीत सिंह दीक्षित, रोहिणी शर्मा, शुभम गोयल, नमन कुमार, गार्गी यादव, सुरभि सिंह, सुबी शाश्वत, प्रियंका हुड्डा, अनुज कुमार, रूपाली चौधरी, उर्मिला शरण, आशुतोष कुमार रंजन, विवेक कुमार, विनीत कुमार, आर्यन भट्ट, मुदस्सिर मासूम, शिल्पा रंजन, अर्पणा सिंह, अनुराग कुमार, दीपक कुमार, मोहम्मद फरमान, गणेश कुमार जायसवाल, विजेंद्र तो कहाँ बच गया? विजेंद्र सर तो कहाँ है? Thank you all. Thank you, sir. Thank you all. Thank you, ma'am. I would request Professor Dr. Ankita Patel ma'am for give a vote of thanks.
लगा दे सर
Dr. Mata ma'am to give the vote of thanks. Good afternoon, everyone. As we conclude this GIAN course, it's my privilege to extend a heartfelt thanks on behalf of Department of Electrical Engineering, DTU, my sincere gratitude to all the dignitaries on the dais, Professor Madhusudan sir, course coordinator GIAN for his vision and constant guidance, Professor Rachna Garg ma'am, local coordinator GIAN, and head of department for his continuous support throughout the program, Professor Prakti Kumar sir, Honorable Vice Chancellor, Shri Mata Vaishno Devi University, Professor Vishal Verma sir, Dean Alumni Affairs, and my special thanks to Professor Ambrish Chandra, our distinguished international faculty. Sir, your sessions have been extremely enriching. Over the past 5 days, participants have gained clear insights into power quality challenges, controller design, mitigation techniques, and grid integration issues, precisely the objectives that we set out to achieve. The practical examples and case studies you shared will certainly help them in their research, academic work, and future professional roles. I would like to thank Professor Anjali Agarwal ma'am for, she is the alumni of our university, Delhi Technological University, from Electronics and Communication Engineering. She has just received International Faculty Alumnus Award, and Professor and Mr. Rajiv Agarwal sir.
Ex-MTPC. DG 1977. And I'm presently the Vice President of the DG Alumni Association.
Thank you, sir, for your presence here. And to all our participants, thank you for your enthusiasm and active engagement, which made this course truly meaningful. I also extend my appreciation to all our faculty colleagues, administrative and technical staff, and especially the sport and hospitality teams for managing the food, logistics, and arrangement so smoothly throughout the program. Thank you once again to everyone who contribute to the success of the GIAN course. Wishing you all the best. Thanks.
Now we can go for
Group photo, yes, sir. Now let's have the group photograph.
That is the last activity, I hope.
Yes, sir.
One before that, I would tell you that Delhi Polytechnic, DTU, is one of the best institutions in all the country, and we are proud of that. Many of our alumni, they are settled abroad, and they have done well. Recently, Professor Vinod Dham, our faculty, Vinod Dham, he got the Padma Vibhushan also award. So you must be knowing his father well, Intel Pentium. Similarly, we have also Padam Shri. We have also Raghbir Singh Bola, who was Olympian, twice Olympian hockey. So you will have great personality from DC, DTU, like many other colleges. Thank you very much.
And I also want to tell you that at the opening ceremony of this course, the Honorable Vice Chancellor, Professor Pratik Sharma, he declared that Electrical Engineering Department is the best department in DTU. This is what he said.
आओ सर आप इधर आ जाओ
Hold on.